Hello. Today we're going to be talking about motion, and that's found in Chapter 2, Section 1 of our physics books. Let's get started on motion. The first thing that we need to know about motion is that motion and position have definite terms, and we need to understand those terms. So the first term that we're going to talk about is motion. The definition for motion is a change in an object's position relative to a reference point. And a lot of times we have to be very precise when we talk about physics because sometimes the language that we use isn't precise. Like, how do you know something is moving? Well, I can see it move. Well, that doesn't necessarily work because we need to have a specific set frame of reference for that motion. And that's why we talk about it relative to a reference point. So that whole phrase of I see it moving, the reference point would be your position, right, versus the relative object or motion that you see in that object. So what is a reference point? A reference point is a designated point where an observation or a measurement is taken. And you can think about this as a yardstick or a ruler. You use a reference point, you always start at the very first point of the ruler. You don't start halfway through the ruler to make a measurement. You start at the first point, the first line of measurement. And that's kind of what we do that for. The reason we do that for is we can compare data. If we take multiple measurements from the same point of different objects, that should be roughly the same, and then we can use that to compare data. What is the word frame of reference? I mentioned that before. A frame of reference is like a coordinate system in which the position of an object is measured. What that means is that a lot of times, say for instance, you have a grid, and you can put things on a grid map, or you graph it on a graphing paper, and those lines allow us to use a coordinate system. But frame of reference is also talks about the area or the objects that are involved in that area that we're measuring things from. So we just try to remember it's a coordinate system, and the coordinate system is an XY grid used to locate and place objects. This is the easiest way to show motion, position, all that kind of stuff is when you have a graph paper and it's labeled X and Y. And then we can talk about that. So one of the first things we're going to look at is this little picture right here. And it shows two different pictures. And the question is, how do you know the mail truck has moved? And what you want to do is you want to find different points of references. For instance, you could say, okay, well, this tree and this mailbox here is my frame of reference. And then if I look back down here, well, now obviously he has moved from these 2 points. Well, but if you look down here, there's a lot of other trees and possible mailboxes there. So we might want to expand our frame of reference a little bit. Well, you can compare the houses here in the background. These houses here, notice that they're the same. So that means the camera didn't move because the background, this tree with the funny branch out here, this house turned this way, those are the same on both pictures. So we know that the camera didn't move. We know that the mail truck has moved. That's one of the things we got to be very careful of because sometimes the frame of reference will move and it looks like there's motion, but the only motion was the fact that we went from one frame of reference to another frame of reference. Kind of tricky, but that's just to kind of give an idea of how motion is all relative depending on the objects that are there. So here's what we talked about the coordinate system. We have the X's and the Y's. And so we look at this, and all the time when we use a coordinate system, we always put the X first and the Y last. Remember, the X is on the bottom, and the Y is on the left side, the vertical. Okay, so where is the location of the red car? Well, I see a red car right here, so I would say, okay, it's -2, and the Y is 2. Right? The school bus, very similar. Notice now, if we did our Y-axis before the X-axis, notice this is X2 and Y -2, it's the exact opposite of the red car. So you always want to make sure that you put the X-axis first. Okay? And for instance, how about the post office? Well, the post office is very simple. It's 0, 0. That means it's the middle of our coordinate system. Okay? So let's talk about changes in position. The first way we talk about change in position is a distance. This is a measurement from one point to another. Distance is different than displacement. Displacement is the distance and the direction of an object's change in position. For instance, what if I went to the store for my house and then I came back to my house? What was my distance? Well, if I started at 1 and ended at 1, that means my distance didn't change. However, totally my displacement did because I went to the store and back. So it's added together. Okay. So it's just language that we're going to talk about. Again, can distance and displacement be different? Of course it can. Here's another example. It shows a runner, right? Notice that the distance the runner is running, right? He runs from the starting line to the 50-meter mark, and he turns around and he comes running back to the 20-meter mark. Well, his displacement, all right, we know is a total of 70 meters. Actually 80 meters, I apologize, 50 plus 30. But his distance from the starting line is only 20 meters, okay? Because that's where he started and that's where he stopped. It doesn't take into account the fact that he went all the way down to the 50-meter mark and then turned around and came back, okay? So that's how displacement and distance can be different. And we'll have a little bit of practice on that. So when we add displacements, distances can be added to get a total distance. But what about if they're in different directions? How does that work? Well, there's just 3 rules that we have for adding displacements, okay? So displacements in the same direction are added. Obviously, if I went 5 meter east, took a break, and then took another 5 meter east, I add those distances up to make my displacement 10 meters east, okay? And notice that is a distance and direction. So be very careful when you're doing displacements that you have distance and direction. That's part of the definition. Okay? If there are displacements in the opposite direction, you subtract them. For instance, I went 5 meters east, right? And then I went 5 meters west. Well, my total distance then is 5 meters or 10 meters to the east, okay? Because we subtract them. I apologize, I did that backwards. Okay, we go 5 minus 5 is 0. So I'm at 5 meters east and then 5 meters west. My displacement is 0. My distance is 10 meters. Okay, so we subtract the displacements in the opposite direction. Okay, the distance I traveled was total 10 meters, but my ending spot, my displacement is 0. And then displacements are not in the same direction or opposite directions. We can't directly add or subtract them. Notice if I went 4 meters east and then I turned and went 3 meters north, all right, my east measurement and west measurement doesn't change, but now I've gone north. So this is when we find the hypotenuse, which is a squared plus b squared equals c squared. Okay, and we'll have some practice with that. So these are the 3 rules. If they're in the same direction, you add them. If they're opposite directions, you subtract them. And if they're not in the same directions or opposites, then we have to use the hypotenuse. Speed. Let's now talk about speed. Speed is the distance of an object that travels per unit of time. Okay? So we have a formula that kind of explains this a little bit easier. So speed is distance divided by time. That's the easiest way to remember that. Also known as S equals D divided by T. So it's the distance you travel and then how long it takes you to travel. And the basic measurements of those is meters and seconds. We don't use minutes or hours, we use seconds, okay? That's the base measurement is time. In the metric system, we use seconds, okay? And we can convert, and that's easily done if you just remember some conversion factors. All right, so again, speed is distance divided by time. It's the distance an object travels per unit of time. Excuse me. Now here are some definitions that you want to write down. Types of speed, constant speed. This means that we're moving with neither acceleration or deceleration. We're not slowing down. It's like when you hit the road and your dad hits cruise control on the car and the car maintains that 70 miles per hour. Okay? Acceleration is different. Acceleration is when speed is increasing over time. We're getting faster. The easiest way to explain this is you're accelerating. We push your foot on the gas pedal and you start going faster and faster and faster. Okay? Deceleration is the opposite of that. That is speed decreasing over time. We also can call that negative acceleration, okay? Because it's the opposite of acceleration. What is changing speed? Changing speed means usually speed is not constant. It's a mixture of accelerations, constant speeds, and deceleration. Think about the travel from your home to school today. All right, there was obviously a lot of different changing speeds. The bus just didn't like swing by your house and not stop, and you had to jump on board while it was doing 35 miles an hour down the road, and it maintained 35 miles per hour through all the stop signs. That obviously didn't happen. There was stopping, slowing down, braking for other cars, all kinds of things of that nature. So that is what we call changing speed. Okay? So our average speed is the total distance divided by the total time. This is how we figure out the changing speed, because obviously if we're not taking constant measurements to know our different speeds and all that kind of stuff, what we do is we find an average speed. Okay? And this is the total distance divided by the total time. Okay? And instantaneous speed is the last type of speed we'll talk about, and that is speed at a given point of time. It's the speed right now. Okay? And that the easiest way to explain that is you look at the speedometer, and the speedometer gives you instant speed. It's the speed right now. This is the speed that you're going. Okay? And I apologize, I forgot about velocity. Velocity is speed and direction of an object, okay? So velocity combines speed and direction, okay? Speed by itself, it's not velocity. Direction by itself, not velocity. You have to have speed and direction. We'll talk about more about velocity in the coming chapters, okay? Let's look at a couple of practice problems where we look at speed. So we're going to calculate the speed of a car. The car is traveling at a constant speed, and it covers a distance of 750 meters in 25 seconds. Well, if we look at our formula, we have two knowns, and we're going to figure out the third. We know the distance, which is 700 meters, and we know the time. So our formula is speed divided by speed equals distance divided by time. And we look at it, we have 750 meters divided by 25 seconds. And that gives us 30 meters per second was our constant speed. So as long as you know your knowns and you remember the formula, and again, you always have your formula available for you, you can figure out the problems from there. And if it's not that straightforward, we just do a little bit of algebra and swap some of those around and we'll figure it out. The next one we're going to talk about is graphing motion. So there are two different types of graphs that we have with graphing motion. And the first one is speed over distance. So speed is on our y-axis, distance is on the x-axis. And you'll notice down here as the distance gets farther, our speed is constantly changing. So we talk about how there's accelerations, there's decelerations mixed in with constant speeds to get to a certain point. Okay. And again, this kind of shows how if you're walking or maybe riding a bicycle, that kind of shows how things work, right? Notice how our speed is slowing down to 0 on the distance here, because that means we're stopping for red light. So it's speed over distance. The other one that's mostly confused with that one is a distance over time graph. Notice how we have distance on the y-axis and time on the x-axis. There's no speed in here. Okay, so that's probably the first giveaway that this isn't the graph that we had before. This is a distance over time graph. And notice as the time increases, so does the distance if there's motion. If there's no motion, notice the distance doesn't change here. That means the person is stopped for 10 minutes, 10 to 20. Okay, there's no motion here. A flat line represents no motion. Okay, and you'll see how our acceleration shows here, distance over time. Okay, and we also calculate speed with the distance over time graph because again, speed equals distance divided by time. So we can actually calculate the speed on individual points in here. All right.